A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. You ever look at a model card on Hugging Face? Maybe you are trying to find a version of Llama 3 that fits on your machine, and it looks like someone fell asleep on their keyboard. You see these strings like Q4_K_M or Q5_K_S, and it feels like you need a secret decoder ring just to figure out if your GPU is going to explode or not.
It really does look like a bunch of random noise if you are not steeped in the GitHub issues of the last 2 years. But those letters and numbers are actually a very precise map of how much brain power you are trading away for speed and memory. It is the literal foundation of the local AI movement. I am Herman Poppleberry, by the way, and today we are stripping away the mystery of quantization.
And I am Corn. Today's prompt from Daniel is about exactly this: the alphabet soup of model quantization and where tools like Unsloth fit into the mix. We are basically talking about how to take a massive multi-hundred gigabyte AI model and squeeze it down until it fits on a single graphics card without turning it into a complete idiot. Also, just a quick heads up for the nerds in the back, today's episode is powered by Google Gemini 3 Flash.
Which is fitting because we are talking about model efficiency. If you look at the raw weights of a top-tier model like Llama 370B in its original format, you are looking at something like 140 gigabytes of data just to load the weights, that is, using 16-bit precision. If you went back to the old-school 32-bit floating point, or FP32, you would need nearly 300 gigabytes of video RAM. Nobody has that at home unless they have a server rack in their basement.
Right, and even a 4090 only has 24 gigabytes. So, without quantization, the 70 billion parameter models, the ones that actually feel smart, would be completely off limits to everyone except big tech companies. It is the difference between running a genius on your desk or just talking to a very fast, very small model that barely remembers its own name.
That is the core of it. Quantization is the art of reducing numerical precision. In a computer, these model weights are stored as numbers. Usually, they start as 32-bit floats, which are incredibly precise. Think of it like measuring the distance between two cities down to the millimeter. It is accurate, but do you really need that level of detail to drive there? Probably not. Quantization says, let us measure in meters instead, or maybe even kilometers. You save a ton of space, and as long as you are careful, you still get to the right city.
So, Unsloth enters the chat. I have seen their name everywhere lately. They seem to be the darlings of the fine-tuning world because they make this high-level math look like a one-click install. Where do they actually sit in this pipeline? Are they the ones doing the squeezing? Or are they just the ones making the training faster so we can squeeze it later?
They are doing both, honestly. Unsloth is a library that specifically optimizes the kernels, the actual mathematical operations that happen during fine-tuning. They rewrote these operations in a language called Triton, which is much more efficient than the standard code most models use. They can make training 2 to 5 times faster while using 70% less memory. But the pro move they enabled is something called QLoRa, or Quantized Low-Rank Adaptation. It means you can take a model that has already been squeezed down to 4 bits and fine-tune it further without ever having to blow it back up to its full size.
That is wild. It is like trying to do surgery on someone while they are wearing a corset rather than making them take it off first. It saves a massive amount of space during the process. But let us get into the actual soup. When I see Q4_K_M on a GGUF file, what am I actually looking at? Break down the hierarchy for me, because I know the bits matter, but those letters at the end feel like a grade in school.
Let's start with the bit depth, that is the Q number. Q8 is 8-bit. It is almost indistinguishable from the original 16-bit model. You lose maybe 0.5% of accuracy, but you cut the size in half, 1 byte per parameter. Then you have Q4, which is the industry's sweet spot. It is 4-bit. You are cutting the model size by 75%, but you are still keeping about 95% of the intelligence. It is the magic threshold where a 70 billion parameter model finally fits on a consumer-grade setup.
And then you go lower and things start to get weird? I have seen Q2 models, and they usually respond like they have had a very long night at the pub.
Q2 is extreme. You are using only 2 bits per weight. For a small model, like an 8 billion parameter model, Q2 is basically unusable. It loses the plot constantly. However, for a massive model like a 400 billion parameter beast, Q2 can actually be surprisingly coherent because the sheer scale of the model compensates for the lack of precision in each individual weight. But for most of us, Q4 or Q5 is where you want to live.
Okay, so bit depth is the how much. What about the how? The GGUF format has these suffixes like K_M or K_S. I assume M is medium and S is small, but what are they actually doing differently? If I have a 24 gigabyte card, why would I pick the small version of a 4-bit model instead of the medium one?
This is where it gets clever. The K stands for K means quantization. Instead of just rounding every number to the nearest lower precision value, K means looks at clusters of weights. It says, okay, these 1,000 numbers are all pretty similar, let's represent them with one specific value from a lookup table. It is much more sophisticated than just chopping off decimals.
So it is like a color palette in a GIF? You only have 256 colors, so you pick the best ones to represent the whole image?
That is a great way to think about it. Now, the letters S, M, and L refer to which parts of the model get the most palette. Attention! An LLM is not just one big block of numbers, it has different layers. Some layers, like the attention mechanism and the feed-forward networks, are the brains of the operation. Other layers are less critical. A Q4_K_S or small might quantize almost every layer down to the minimum. A Q4_K_M or medium will look at those critical layers and say, actually, let's keep these at 5-bit or 6-bit precision and squeeze the less important layers even harder to compensate.
So the medium is basically a hybrid. It is a 4-bit model on average, but it is putting the detail where it counts. It is like a high-res photo where the face is sharp but the background is blurry.
Precisely. That is why Q4_K_M is the standard. It almost always has better perplexity, which is the technical measure of how confused a model is than a straight Q4_0 model. It is the same file size, just smarter distribution. If you have the RAM, you always go for the M or L versions over the S.
That makes sense. But GGUF is just one format. If I'm looking at Hugging Face, I also see GPTQ, AWQ, and this new one, EXL2. If I have an NVIDIA card, I feel like I'm being pulled in 4 different directions. How do I choose between the format that runs on my CPU and the one that is optimized for my GPU?
This is the great divide in the community. GGUF is the king of flexibility. It was created for llama.cpp, and its superpower is offloading. If you have 16 gigabytes of VRAM but the model is 20 gigabytes, GGUF lets you put 16 on the GPU and the remaining 4 on your system RAM. It will be slower, but it will run. It is also the only real choice for Mac users on Apple Silicon.
So GGUF is the "it just works" option. What about GPTQ? I remember that being the big thing about a year ago.
GPTQ is GPU only. It is a one-shot quantization method. It is very fast on NVIDIA cards because it is designed to utilize the tensor cores perfectly, but it is brittle. You cannot offload parts of it to your system RAM effectively. If it doesn't fit in your VRAM, it just won't run. AWQ, or Activation-Aware Weight Quantization, is like the smart version of GPTQ. It actually looks at which weights are the most active when the model is running, the salient weights, and it protects them from being squeezed too hard. It usually beats GPTQ in quality for the same size.
And EXL2? That one sounds like a high-performance oil for a racing car.
It kind of is. EXL2 is built specifically for the XLLama V2 loader. It is arguably the fastest way to run LLMs on NVIDIA hardware. The cool thing about EXL2 is that it is not limited to whole numbers. You can quantize a model to exactly 4.65 bits per weight if that is what it takes to perfectly fill your 24 gigabyte VRAM. It is incredibly granular. But again, it is NVIDIA only, and it does not like to share with system RAM.
It feels like we are in this era where the software is finally catching up to the hardware constraints. I mean, Unsloth being able to do this on a free Google Colab instance is kind of mind-blowing. I remember when fine-tuning a 7 billion parameter model required a professional workstation and a lot of prayer. Now you can do it in a browser tab.
It really has democratized the technology. And what Unsloth did that was so smart was integrating these quantization methods into the training itself. Usually, you would train in high precision, save the model, and then run a separate script to quantize it for use. Unsloth lets you do 4-bit gradient checkpointing. They have basically optimized the math so that the corset we talked about earlier is actually part of the surgical procedure. It is not just a post-processing step anymore.
So, if I'm a developer and I want to build a tool that uses a local model, my workflow is basically use Unsloth to fine-tune a model on my specific data, then export it as a GGUF or EXL2, and then ship it to users. But here is the big question. Does the brain damage from quantization actually matter in the real world? If I am building a medical bot or a coding assistant, am I losing critical logic when I go from 16-bit down to 4-bit?
That is the million-dollar question. The research shows that for general conversation, the loss is almost unnoticeable. But for complex reasoning like high-level math or very subtle coding logic, the quantization error can manifest as a lack of robustness. The model might get the answer right 90% of the time in 16-bit, but only 85% of the time in 4-bit.
That 5% doesn't sound like much until it is the 5% that keeps your bridge from falling down.
Right. But here is the counterintuitive part that most experts agree on. A 70 billion parameter model at 4-bit precision almost always beats an 8 billion parameter model at full 16-bit precision. Scale is the ultimate cheat code. If you have to choose between a small, perfect brain and a massive, slightly blurry brain, you take the big one every single time. It just has more internal connections to draw from.
That is a great rule of thumb. It is better to have a genius with a slight concussion than a very focused elementary school student. So, when we look at the numbers and the perplexity scores, how much of this is just academic posturing versus actual performance? I have seen people argue over a 0.01 difference in perplexity. Does that actually translate to the model being better at writing a poem?
In my experience, those tiny differences in perplexity are mostly for leaderboard bragging rights. However, once you drop below 4 bits into the 3-bit or 2-bit range, the perplexity starts to skyrocket. That is, when you see the cliff. The model starts repeating itself, it loses track of the conversation context, and it starts hallucinating in ways that are just weird, not even plausible.
I have seen that. It starts talking in circles or just starts spitting out random characters. It is like watching a digital stroke in real time. But let's talk about the hardware side. If I am running a Mac Mini with 64 gigabytes of RAM, I am probably looking at GGUF because Apple's unified memory handles it so well. Does quantization work differently on Apple Silicon than it does on NVIDIA?
The math is the same, but the way the hardware accesses the memory is the game changer. On an NVIDIA card, you have incredibly fast VRAM, but it is a separate pool from your system RAM. When you run out, you hit a wall. On a Mac, since the CPU and GPU share the same pool of memory, you can run much larger quantized models than you could on a PC with a mid-range GPU. This is why the Mac has become the unofficial home of the local 70B. You can run a 70 billion parameter model at Q4 precision on a Mac with 32 or 64 gigabytes of RAM quite comfortably.
And that is where the GGUF format really shines. I think a lot of people don't realize that GGUF actually stands for GPT Generated Unified Format. It was designed to be a single file that contains everything: the weights, the metadata, the tokenizer info. Before that, we had GGML, which was a nightmare, because you had to keep track of 5 different files just to get the thing to boot.
And GGUF is extensible. It allows developers to add new features without breaking old models. It is why we can have things like look-ahead decoding or classifier-free guidance added to the format without everyone needing to re-download their entire library. It is a very robust ecosystem.
Let's circle back to Unsloth for a second. They recently had a big update in early 26 that added support for even more quantization methods and better CUDA optimization. It feels like they are trying to stay ahead of the curve as models get bigger. What is the end game for a tool like that? Is it just making things faster, or are they trying to change how we think about model weights entirely?
I think they are aiming for zero loss efficiency. Their goal is to make the overhead of training so low that the hardware is the only bottleneck left. They want to get to a point where the difference between a base model and a quantized model is purely a choice made at the very last millisecond of execution. They are also working on dynamic quantization, where the model could potentially change its precision on the fly depending on how hard the question is.
Like shifting gears on a bike. If you are just saying hello, it uses 2 bits. If you are asking it to solve a physics problem, it ramps up to 16 bits. That would be incredible for battery life on mobile devices.
We are already seeing the beginnings of that with things like MOE or mixture of experts models. Not every part of the model needs to be awake for every query. If you combine that with dynamic quantization, you could have a model that is technically massive but runs on the power of a toaster.
So, if we are looking at practical takeaways for someone starting out today, they have just discovered Hugging Face, they have a gaming PC, and they want to run something cool. What is the Korn and Herman recommended starting point for the alphabet soup?
Start with GGUF and a loader like LM Studio or Olama. It is the easiest entry point. For the model, look for the Q4_K_M version of Lamama 3 or whatever the latest Mistral variant is. It is the gold standard for a reason. You get the most bang for your buck in terms of intelligence versus file size.
And if they want to get their hands dirty with fine-tuning,
go straight to Unsloth. Don't even bother with the standard Hugging Face PEFT library unless you have a specific reason to. Unsloth's notebooks are designed to work on free hardware, and they handle all the messy quantization math for you behind the scenes. You just pick your bit depth and hit run. It is the closest thing we have to a cheat code for AI development right now.
I love that. It is rare in tech that something gets both faster and easier at the same time. Usually you have to pick one. But Unsloth seems to have found a way to give us both.
It is because they went back to the basics. They didn't just build another layer on top of old code, they went down to the level of the GPU kernels and said, this math is being done inefficiently, let's fix it. It is a reminder that even in the world of cutting-edge AI, good old-fashioned software engineering still matters.
There is something satisfying about that. We have these trillion-parameter dreams, but they still rely on someone being really good at writing efficient CUDA kernels. It keeps the whole thing grounded.
It really does. And the more we optimize these weights, the more we realize that information density is much higher than we thought. We used to think you needed 32 bits to store a thought. Turns out you can do it in 4, maybe even less.
That is a bit humbling, isn't it? My entire personality might just be a 2-bit quantization of a much more complex system.
I'm not going to touch that one, Korn. I'll stick to the LLMs.
Fair enough. But seriously, the move toward local AI is so dependent on this stuff. If we want privacy, if we want to run these things without a subscription, we have to keep squeezing the soup. We have to keep making these models smaller and smarter.
And we are. The gap between cloud AI and local AI is shrinking every month. A year ago, running a decent model locally was a hobby for enthusiasts. Today, with GGUF and a decent Mac or PC, you can have a private assistant that rivaled GPT-4 from a couple of years ago. That is insane progress.
It is, and it makes you wonder where we will be in another 2 years. Maybe we will be talking about Q0.5 and models that run on a digital watch.
I wouldn't bet against it. The math is only getting better.
Well, I think we have successfully demystified the alphabet soup. Or at least we have given everyone a fork to eat it with. It really comes down to finding that sweet spot, usually Q4, and using tools like Unsloth to make the heavy lifting feel a bit lighter.
It is an exciting time to be a nerd. The barriers to entry are just melting away.
They really are. And I think that's a good place to wrap this one up. We have covered the bits, the letters, the formats, and why a sloth and a donkey can run a 70 billion parameter model on their laptops.
Speak for yourself, Corn. I've got a cluster in the barn.
Of course you do. Big thanks to our producer, Hilbert Flumingtop, for keeping the bits and bytes in order behind the scenes. And a massive thank you to Modell for providing the GPU credits that power our exploration of these massive models.
This has been My Weird Prompts. If you found this deep dive helpful, or if you just want to see more of our weird explorations, search for My Weird Prompts on Telegram to get notified when we drop new episodes.
We will be back soon with more of Daniel's prompts. Until then, keep your precision high and your perplexity low.
Or just quantize it and see what happens. Goodbye.
Bye. This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the close from sloth, from man, from long-eared host. My Weird Prompts, until next time, stay curious, keep